this video is to review the models of the atoms that we talked about in class. The first model we talked about was Democritus, or Dalton's model of the atom. You see here that this model is like a billiard ball. The atom was viewed as an indivisible ball that had mass. Notice you don't see any of the subatomic particles like protons, neutrons, and electrons. As time goes on, the model of the atom changes because J.J. Thompson discovers electrons. He then proposes his model of the atom. This model has a blob of positive stuff that the electrons, his newly discovered negative particle, are contained in. He knows that there must be positive and negative because atoms are neutral. If you watch the simulation, you see that Thomson's model allows most of the light to go through unchanged, but the electron occasionally gets hit by light and some light comes out. Thomson's evidence changed the model of the atom. After a while, after J.J. Thompson, a scientist named Ernest Rutherford does an experiment. He fires alpha particles, which are the same as the nucleus of a helium atom, meaning they have 2 protons and 2 neutrons, at a thin foil of gold. What he sees surprises him. He expects that if Thomson's model is correct, the alpha particles should all go straight through. They do not, though. In fact, some bounce straight back. So imagine, to get an idea of what this is, if you shot a Kleenex that you blow your nose with a gun, and the bullet bounced right back at you. That'd be really shocking. But that's what Rutherford experienced, but at the nanoscale. So when he sees this, Rutherford proposes that the atom must have a positive center. Thus, we have the nucleus. He also says that the rest of the atom must be empty space because many of the alpha particles he fired go straight through. His evidence now changes the model of the atom. And after Rutherford, we have Bohr, who takes the idea of the positive nucleus and tries to explain some new evidence. So when scientists were looking at the light coming out of specific types of gas, like hydrogen gas, so this might be something like if you looked at a neon light that you see on signs. So when they did this, they only got certain colors of light when they looked at that through a prism. Those certain colors have very specific energies. Bohr then suggests that those colors of light must be coming from electrons at different energy levels being excited up and then returning to their ground state. Based on his evidence of spectral lines and emissions from atoms, he proposes his own model. So that model can be seen in this simulation, or we can think of it like a bunch of energy levels on a graph. It's just a model, so remember that it's not actually what the atom looks like. And then after Bohr, some scientists start to notice that his model only really works on certain atoms. But it doesn't hold true for all of the atoms, so they investigate, they get more evidence, and then Ernst Schrodinger comes up with an equation that seems to predict most of the evidence that they're seeing. And that is the model that we currently have. So if we look at the simulation over here of what really happens, we see that our evidence, what we see is happening, is supported by the Bohr model and the modern quantum mechanical model. Right now, we can't tell the difference without some more information.